Welcome to Kroner's e-learning module, Coriolis Mass Flow Meters. This module is the second of two parts and continues to provide some basic knowledge of Coriolis flow meters. As an introduction to this module, we would like to tell you about the learning targets for this second module. Having completed the first module, this second module continues to provide training on the subject of Coriolis mass flow meters. When you have finished this second module, you will have an understanding of selecting mass flow meters to suit process fluids, and have reviewed additional advice on some industry constraints for the selection of Coriolis mass flow meters. You will also see how sizing and selecting mass flow meters for gas applications differs from that of liquids. You will be made aware of the high accuracy capability of Coriolis mass flow meters. You will appreciate the benefits and advantages along with the restrictions of using Coriolis meters. You will be made familiar with the most important installation guidance for liquid and gas applications. Finally, you will be provided with examples of applications by industry using Coriolis meters for both liquids and gases. So let's continue from where the first module finished and begin with selection for process fluid properties. Some applications require special consideration due to the process fluid's properties. Abrasive fluids, such as mineral slurries, paper pulp or fruit juices and sugarcane, will erode the very thin measuring tubes. From experience, we suggest that the meter be sized to limit the flow velocity to below 5 meters per second, and to avoid irregular erosion, install the meter vertically. But to avoid sedimentation where the solids can coat the measuring tube wall, keep the flow velocity above 2 meters per second. Use a single straight tube meter with a titanium measuring tube wherever possible to minimize turbulence and maximize wear resistance. To limit the erosion of the exposed flange raised face, install transition pieces. These must be sized to suit the exact customer pipe size and the meter to which it is being installed. Similarly, viscous liquids or shear sensitive fluids are best measured using a single straight tube meter to minimize pressure drop and limit the stresses imposed on the shear sensitive fluid. Viscous fluids can exhibit reverse flow caused by the bends in bent tube meters. This effect is similar to the eddies or vortices on the bends of a river. Coriolis twin tube meters are often better suited to gas applications due to the wider turndown for lower flow rates and the reduced flow velocities. However, single tube meters may still be appropriate. Especially for gases, check sizing carefully across the full range of operating conditions, including minimum operating pressure and maximum temperature. Customers and industries often set their own operating maximum flow velocities. However, for gases, we advise practical maximum conditions of 80 to 100 meters per second. Fluids can also have process restrictions. Hydrocarbon liquids are often restricted to below 8 meters per second in the API guidelines. However, Coriolis mass flow meters are designed to be safe above this historical flow rate. Also, milk products are limited to below 3 meters per second due to churning, which can cause milk to turn sour or curdle. Let us now have a brief look at an important physical property of gases which has to be considered for the measurement of gases: compressibility. The distance between the individual molecules is considerably greater in gases than in liquids and solids. Gases always fill the available space evenly and completely. Under pressure, gases can be compressed much more than liquids. let us compare the compressibility of water and air. To reduce the volume of water by 1%, the pressure must be raised by 200 bar, whereas an increase of 0.02 bar would be enough in the case of air. Ideal gases can be calculated using the ideal gas law. The behavior of real gases is then described using the compressibility factor K. Having now reminded you about the compressibility of gases, we can use this property to demonstrate the influence on Coriolis mass flow measurement. In the meter selection, we have to carefully consider the sizing for the measurement of gases. We have to consider gas applications differently because Coriolis meters were initially developed for measurement of liquids. The densities of liquids are typically between 0.8 kilograms per litre and 1.2 kilograms per litre, whereas the operating densities of gases are between 5 grams per litre and 200 grams per litre. Therefore, for liquids, the value of the volume is on parity to that of the mass, but for gases, the volume value is many times greater than that of the mass flow value. To suit the operating range of a Coriolis mass flow meter, we can use the compressibility of gases to raise the pressure and increase the mass flow rate. However, the low density of gases still results in very high pressure drops compared to a liquid at the same mass flow rate. Also, when the mass flow rate increases, the gas velocity increases to the point where choked flow occurs, even though the mass flow rate capability of the instrument has not been reached. Let's have a look at an example. An Optimas 7000 titanium size DN15 with water as a process fluid compared to carbon dioxide gas, both at a mass flow rate of 2000 kilograms per hour. At 16 bar pressure for carbon dioxide, with the mass flow of 2000 kilograms per hour, the flow velocity is 112 meters per second, which would be considered as approaching choked flow conditions. Yet for water, the velocity is still only 3 meters per second. Similarly, the pressure drop is nearly 40 times higher for the carbon dioxide compared to water at 2000 kilograms per hour. Due to the compressibility of gases, if operating pressure is increased to 30 bar, then the flow velocity will reduce to 58 meters per second, and the pressure drop will again reduce, while the mass flow rate remains at 2000 kilograms per hour. When sizing for gas applications, ensure the customer data states the flow rate and density as normalized or operational. Normalized conditions are shown in the table. For Europe, this is referenced to 1.013 bar at 0 degrees Celsius, 273 Kelvin, DIN 1343. And for international norm, 1.013 bar at 15 degrees Celsius, 288 Kelvin, ISO 13443. Knowing an accurate minimum operating pressure is essential for verifying the suitability of a Coriolis mass flow meter, as applications become more difficult below 15 kilograms per cubic meter operating density and need to be sized carefully. This table provides a general summary of common gases and the minimum operating pressures to achieve 15 kilograms per cubic meter. For hydrogen, with a normalized density of 0.089 kilograms per normalized cubic meter, the pressure needs to be above 194 bar. For methane, with a normalized density of 0.71 kilograms per normalized cubic meter, the pressure needs to be above 22 bar. Similarly, for air with a normalized density of 1.25 kilograms per normalized cubic meter, the pressure needs to be above 12 bar. And a final example. Carbon dioxide with a normalized density of 1.95 kilograms per normalized cubic meter, the pressure needs to be above 8 bar. In summary, for gases, due to the high volume flow rate, resulting in high flow velocities, the meters selected for gas applications are sized 1 or 2 meters larger than that for a liquid at an equivalent mass flow rate. Sizing for gases is based on flow velocity at maximum flow rate and accuracy requirement at minimum flow rate. Most gas applications will result in the meter sized at the lower end of the operating range. If the meter is undersized, then the meter may tend to choke, resulting in pressure pulsing and high turbulence. Let's now have a look at the accuracy for mass flow measurement. Mass flow meters offer a highly accurate measurement of liquids and are often quoted as plus or minus 0.1%. The volume flow accuracy of the same meter is quoted as plus or minus 0.15%. Yet for gases, the same meter is only quoted to better than plus or minus 0.35%. This is due to the increased effect of the zero stability on the measurement reading, coupled with the meter having to be sized 1 or 2 sizes larger than for a liquid operating on the same mass flow rate. Mass flow meters independently measure the density of liquids. Density accuracy is restricted to applications in the range 400 to 3000 kilograms per cubic meter. Therefore, Coriolis meters are not suitable for gas density measurement. Coriolis meter density measurement is generally accurate to 2 kilograms per cubic meter as calibrated, or after an on-site density calibration to 0.5 kilograms per cubic meter. The temperature measurement in steady state conditions is accurate to within 1 degree Celsius. Why use Coriolis mass flow meters? Coriolis mass flow meters are multifunctional instruments, offering direct mass flow measurement for liquid and gas applications, with the versatility to independently measure density and calculate volume flow rate. With the third independent measurement of process temperature, the modern mass flow meter also has the capability to calculate concentration algorithms. The technology has become accepted and now replaces legacy measurement methods. This is due mainly to 2 advantages, that of high accuracy and the low maintenance burden. The Coriolis mass flow measurement principle is independent of process properties of pressure, temperature, or viscosity. Additionally, the measurement principle is also independent of electrical conductivity. The Coriolis principle is also independent of flow profile. Therefore, the Reynolds number is not used in Coriolis flow meter sizing, and inlet and outlet runs are not required. As chemical reactions are calculated using mass, not volume, the Coriolis mass flow meter is ideal for measuring into and out of discrete and continuous chemical processes. With direct mass measurement, the reproducibility of processes is increased. However, what are the alternatives available to the process engineer? The alternatives for mass flow measurement all have significant disadvantages. The first alternative to the Coriolis mass flow meter is a weigh scale, which is also theoretically independent of process volume and temperature. But scales require ongoing calibration and compensation, and are expensive to install. Implementing scales in process applications also requires complex control and peripheral equipment. The second alternative is to use multi-instrument systems. But these volume flow metering technologies require additional sensing, along with integration with a suitable flow computer to provide a calculation of mass flow measurement. The resulting error of the system will be no better than 1.5%, comparison to a Coriolis mass flow meter system with an error of better than plus minus 0.5%. The additional sensors incur additional installation, cabling and energy costs, increasing commissioning costs. And during the system life, the costs of calibration and maintenance will be many times higher than that of a Coriolis mass flow meter. Finally, the number of pipe insertions, along with the other mechanical and electrical interfaces, will result in a lower system safety factor over the single integrated mass flow meter. Now that we have selected a suitable meter for an application, we need to install the meter for optimum process operation. The orientation of the meter in the pipework must first be considered. A horizontal installation is independent of flow direction. For vertical installations, ensure the direction of flow is upward. For an inclined installation, again ensure the direction of flow is upward. Having determined the location for installation and the orientation, ensure vertical installation for drainage or applications with gas bubbles. Prepare the pipework to provide a good zero calibration, density calibration and maintenance. Ensure that isolation valves are installed locally to guarantee a no-flow condition for zero calibration, which is especially important for gas measurement. A bypass loop may also be required for maintenance on continuous processes. For all gas applications, the location of a horizontally installed meter should be high up in the pipework system to stop liquid buildup in the meter. For a vertical mounting, upward flow is preferred, but downward flow is possible. For bent tube meters in a horizontal mounting, install bent tube meters upside down with the measuring tubes above the pipework to prevent buildup of fluid in the measuring tubes when no gas is flowing. These last two installation considerations are the opposite of how a meter should be installed for a liquid process application. Coriolis mass flow meters are used in a wide variety of industries and applications. Below are some examples by industry, but this is by no means a complete portfolio. Such as in the chemical industry, mass flow meters are used primarily where mass balanced processes are required, but they're also used for aggressive corrosive process fluids. Where density is required for process measurement or quality assurance, such as in concentration measurement applications. For custody and physical transfer of base agents or refined products. A second sector is in the oil industry. For custody and physical transfer applications, in custody transfer skids, and as master meters in place of provers. Coriolis is used for viscous oils and crudes, and high paraffin content crudes and fuels where ultrasonic meters are not suitable. These applications include pipeline and leak control management, oil and water separation, where density is also used for process control. In the pharmaceutical and biological sector, where again mass balanced processes are essential. However, Coriolis mass flow is also used in coating processes of tablets and caplets, vitamin extraction and processing, purified water which is non-conductive, water for injection, WFI, and ultra-purified water used for medical applications, CIP and SIP management. Another key sector is the food and beverage industry, especially for filling machines and batch processes. Also for accurate density and calculated concentration measurement for quality and process control. Mass flow meters offer options for hygienic and sanitary applications. Mass flow is also used for CIP and SIP management. In the water and wastewater industry, Mass flow meters are used for process additions of additives for drinking water, flocculant addition for wastewater treatment, and measurement of wastewater sludge recovery. And for the pulp and paper industry, coriolis is used for pulp and paper stock management and dosing and mixing of additives. In general industry and processes, coriolis mass flow is used to replace legacy PD or turbine meters, non-conductive fluids where MID meters are not suitable, viscous fluids such as bitumen, abrasive fluids such as in the mining industry, custody and physical transfer such as bunkering, dosing of additives or perfumes, power plant water and liquefied fuel management, fuel and oil consumption measurement on ships and trains. As we have seen, coriolis mass flow meters are also suitable for the measurement of gases in many industry sectors. Process gas measurement, chemical industry, oil and gas production, and the pharmaceutical sector. Site services management in compressed air distribution, CO2 and nitrogen distribution. For the food and beverage industry, the bulk consumption of carbon dioxide and nitrogen in package sealing. Also, carbon dioxide management in breweries. In fuel dispensers and dual distribution networks for compressed natural gas and liquefied fuel such as liquefied petroleum gas and liquefied natural gas. Having completed this second module of coriolis mass flow meters, you will now be able to understand some essential considerations for selecting mass flow meters to suit process fluids, and have some awareness of industrial constraints for the selection of coriolis mass flow meters. You will also know how sizing and selecting mass flow meters for gas applications differs from that of liquids. You will know that coriolis mass flow meters offer the highest accuracy capability. You also appreciate the benefits and advantages, along with knowing some restrictions of using coriolis meters for both liquid and gas measurement. You will now be familiar with the most important installation guidance for both liquid and gas applications. Finally, we have provided you with examples of applications by industry using coriolis meters for liquids and gases.